Okay, good morning once again. So, till the previous class, I was discussing about hydrocarbons, aliphatic and aromatic, the chapter 13. Today is the fifth day of myself transacting the lesson hydrocarbons. Okay. Now, if you remember, in the previous class, I was talking about the properties, the chemical properties of alkynes, like ozonolysis, reaction of alkynes with hot and cold potassium permanganate solution, Bayer's reagent, and all those things. Okay, so today I'd like to continue further in this chapter. Okay, the next chemical property for alkynes is on your screen, that is called polymerization of alkynes. Polymerization, or you can say cyclization. Now, if you look at the first box over here on the screen, you can see over there. If I take three ethyne molecules, okay, if I take ethyne molecules and pass them through a red hot iron tube at 873 Kelvin, 873 Kelvin, then it undergoes polymerization to form an aromatic compound like this, and that is called benzene. Benzene as a molecular formula C6H6. This is the first aromatic compound which we'll be learning after some time. Now, if you look at the second box over here, if I take molecules of propine 1, 2, 3, again pass it through red hot iron tube or copper tube at the same temperature, it is also going to form an aromatic compound. But this aromatic compound is 1,3,5 trimethyl. It is 1,3,5 trimethyl benzene. So I request you all to remember at least these two polymerization reaction of alkynes. It will be very helpful for you later on. Now, so this was the last chemical property of alkynes. After that, let us quickly go through and ponder about the uses of alkynes point wise. The first one over here is acetylene or ethine, which is the simplest alkyne. It is used in torches, acetylene torch for welding, acetylene, not that torch which we use at night, other type of torches for welding purpose. It is used in torches to generate temperatures around 3000 degrees Celsius to weld, to join metal pieces together by generating oxyacetylene flame for welding purpose. Okay, that is the first use. The second use is it is also used as a starting material in the synthesis process used to make polymers, and it is also used as a solvent. It is also used as a solvent. Then the next use is alkynes are generally used in as the starting materials for the manufacture of a large number of organic compounds of industrial importance, such as chloroprene. It's an industrially important compound. Vinyl chloride used for the manufacture of PVC plastic. Okay, chloroprene is also there. Then the next use is alkynes are also highly important parts of some anti-tumor agents. Treatment of cancer. In the treatment of cancer, or if there is any tumor in the body, compounds prepared from acetylene, they are used to deal or fight with those tumor which are being caused in the human body. So these are some general uses of alkynes, which it's better for you all to go through and try to remember. Now, moving to the next slide, we have a test to distinguish between alkanes and alkenes. How to distinguish? We know alkenes, they have a single bond, saturated hydrocarbon. And we also know alkenes, they have at least one double bond, that's why it is called unsaturated. Now, we know alkanes, they undergo substitution reaction. One or more hydrogen is replaced by another atom. And alkenes, they undergo addition reaction. Double bond is broken and atoms added. Now, how to distinguish? This part is important. Now, to distinguish, we can use bromine halogenation. So, when you react alkanes with bromine, the orange color fades slowly in ultraviolet light. It takes time to fade. The orange color of bromine fades very slowly. Whereas if you use alkenes and react with bromine, the orange color disappears immediately and changes to haloalkane, which is colorless. So this is the test. This is the test to distinguish between alkane and alkene. Now, moving further to the next slide. This is over here a test to distinguish between all of them, alkanes, alkenes, and alkynes. Now, over here, if you take an alkyne, look at this alkyne, pentine. If you try to react with bromine, there is no color discharge. The color of bromine is not discharged. It doesn't become colorless at all because there is no reaction. Okay. If you take the next one, an alkene, and react this alkene with bromine in an inert solvent, the color of bromine discharges slowly. It discharges, okay. If you take an alkyne like this, react with bromine in an inert solvent, the color of bromine disappears immediately. So this test is called a bromine water test. Bromine water test to distinguish between the hydrocarbons, alkenes, and alkynes. After that, coming to the next slide over here, this becomes very important, which we have learned slightly in class 10 also in the ICAC. Test for alkynes only with Tollens reagent and ammonical cuprous chloride solution. Now, if you take an alkyne like ethyne and react it with Tollens reagent, what is Tollens reagent? Tollens reagent is ammonical silver nitrate solution. Okay. Now, when you react this Tollens reagent with an alkyne like ethyne, then it produces a white precipitate of silver acetylide along with ammonium nitrate and water. Okay, so this is important for you all. Please learn the equation as well as remember the observation. Okay, this is the observation. This is the test. Okay, the next one over here, it is when you react acetylene with ammonical cuprous chloride solution, then you will get a red colored precipitate due to the formation of copper acetylide, CuC triple bond CCu, precipitate, red colored, very nice colored, red colored precipitate along with ammonium chloride and water. So this is the second test for alkynes. So these two reactions become very, very important for you all with respect to the chemical equations as well as the observations, because there will be direct questions based on this. Okay, so this completes your alkynes today. Now let us move to the next part of the chapter, that is called aromatic hydrocarbons. Aromatic hydrocarbons. Look at that. Aromatic hydrocarbons. What do you see on the screen? Tell me. Aromatic hydrocarbon. What do you see? What do you see on the screen? Come on, speak somebody.
So benzene ring.
You can see a benzene ring, correct? And there are a ring is there, a diagram is there, okay? And there is written benzene ring, chlorination. Do you see chlorination? Do you see nitration?
Yes, sir.
Do you see bromination?
Bromination and
Do you see hydrogenation? Okay, so these are the things we'll be discussing in this part of the chapter in detail. Now, before I jump straight away into this chapter, aromatic hydrocarbons, I would like to first introduce a slide over here and just explain you by drawing some diagrams. Okay, get it is an interesting part of chemistry. Now, for example, if I draw the structural formula of benzene, then I can go ahead drawing like this way, alternate single and double bonds, alternate single and double bonds this way, okay, and then hydrogen, 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 and here also one hydrogen. So this is our benzene. This is our benzene. Okay. The kekule structure, kekule, kekule structure of benzene is drawn like this, simply like this with alternate single and double bonds. Okay. So there are six carbon atoms. There are six carbon atoms and there are six hydrogen atoms in the structure. Now, this is aromatic compound. It is an aromatic compound. Now, let us look at another example. These are all unsaturated hydrocarbons. containing one or more benzene rings. Okay, this is containing one ring. There is one ring. Okay, now I will draw another one. I will draw another one. A bicyclic aromatic compound. Let me try to draw it. Carbon, carbon. Okay, carbon, double bond over here, carbon. Then here another carbon, double bond I'll put over here. Then here I'll draw, extend it further. Double bond here, carbon. Then here single bond. Then double bond over here. Then this is single bond. Okay, then I will give the hydrogens. Hydrogen here, hydrogen here. Okay, 1 2 3 4 over here, hydrogen over here, 1 2 3, one hydrogen here, it's already 4. One hydrogen here, one hydrogen here, one hydrogen here, one hydrogen here. Now look at this, there are two rings. There is one ring, two rings fused together. So this is also a hydrocarbon, unsaturated hydrocarbon. And this compound, if you count the number of carbon atoms, there are 6, 7, and 9, 10. 10 carbon atoms. And if you count the number of hydrogen atoms, there are 6, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 hydrogen atoms. So this is also an aromatic compound. And it is a bicyclic. It is a bicyclic aromatic compound. BICYCLIC, bicyclic aromatic compound. And its name is naphthalene. NAP HTHALEN. It is called naphthalene. It is called naphthalene. So please try to remember benzene. Try to remember naphthalene. Now, if I draw the simple structure of naphthalene, it becomes like this. Like this. See, this is naphthalene. Calculate-like structure. This way, this way. This is naphthalene. This is naphthalene. Okay. Now, let me draw few next example also. The other example. One more. There is one more example. I'll introduce one slide over here. So let me draw another one that is called a tricyclic unsaturated hydrocarbon. So carbon, 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 carbon over here. Then again here carbon, 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 carbon. Done. Then here also carbon, 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 carbon. Done. Okay. So this is a tricyclic. Now I have to put alternate single and double bonds. I'll start from here. Double bond, single bond, double bond, single bond, double bond, single, single, double, double. Then here I can put double, double. So double bonds are placed, alternate single and double bonds. After that, I will give the hydrogen atoms wherever necessary to satisfy the valency 4 for carbon. So hydrogens I'll put like this. Hydrogen here, hydrogen here, hydrogen here, then hydrogen here. Okay, then over here no need, over here also no need, over here hydrogen, over here hydrogen, over here hydrogen, over here hydrogen. Okay, so that's done. Now this compound, it is tricyclic and it is called anthracene. Anthracene. And its molecular formula, it is, if you count the number of carbon atoms, it will be 14, C14H10. It is anthracene, C14H10, and it is a tricyclic unsaturated hydrocarbon which is aromatic in nature. Okay, so these three things you try to remember, it is not so difficult. Okay, now I was talking about Kekule structure. I was talking about the Kekule structure of benzene. Let me clarify that also. The Kekule structure of benzene. Now, with regard to Kekule structure, it is a hexagonal ring. It is a hexagonal ring like this. This is one structure. Another structure I can also draw this way. This time, in this structure one, double bond position is this way. In the other one, I can put it this way. Okay, so these are the Kekule structures for what? For benzene, which is the first aromatic compound in this chapter. Okay, now moving further to few more clarifications over here. Let me take some examples. For example, if I take Cl, if I substitute the benzene ring and I introduce chlorine like this, okay. So this is one chlorobenzene. This is position 1, 2, 3, 4, 5, 6. So carbon 1 and carbon 1 is having chlorine. So it is 1 chloro. This one is 1 chloro benzene. Okay, now if I draw another example over here, Cl. Okay, then I can, shift the position of the double bonds. This is also one chloro, one chlorobenzene. Okay, because please keep in mind these double bonds are always delocalized. They are always delocalized, means they are always moving. They are always moving. They are always moving, shifting from one position to another. That's why we put a dotted lines in the center like this for this compound, which is called chlorobenzene. Okay, now look at the next slide. Let me introduce one more slide over here. Now, if I draw, say if I draw the, the orbital structure of benzene, if I draw the orbital structure of benzene, then I will find that it is like this. It will be like this. I'm drawing it slanting, okay, this way. Carbon, 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 and this carbon, and then I will give the hydrogens this way. Hydrogen, 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 hydrogen. Now, here you please remember this bond which you see, it is a sigma bond. It is a sigma bond which is formed by the overlap of sp2 sp2 hybrid orbitals. Each carbon is sp2 hybridized. Each carbon is sp2 hybridized. So all these bonds are sigma bonds formed by the sp2 overlap of the hybrid orbitals. So this one is sp2 sp2. This one is also sp2 sp2. This one is also sp2 sp2. This is also sp2 sp2. This is also sp2 sp2. That is why there is a delocalization movement of the double bond, which is happening between all the carbon atoms. That's why all these bonds over here, they have a double bond character. Okay, so this is the orbital structure of benzene as explained, after Kekule, with the help of the molecular orbital theory. The molecular orbital theory was successful in explaining the orbital structure of benzene to some extent. Okay, now if you look at the other side, here the sp2 hybrid orbital of this carbon, it is overlapping with the s orbital of what you call hydrogen. Same thing here also. Here sp2 of carbon with 1s orbital of hydrogen. Same thing here also, sp2 of carbon with 1s of hydrogen. It goes on for all the carbon atoms. Okay. Now, uh, what is resonance? Let me explain that also. Resonance, by introducing one more slide over here. Resonance, which I have explained to you in the previous chapters. Resonance means delocalization. Resonance, NANC. Resonance means delocalization of pi electrons. Delocalization. Delocalization of pi electrons. Now I'll just take one example. Of resonance. For example, let me take say hydroxybenzene. Let me take hydroxybenzene this way, having alternate single and double bonds. Now this compound is called hydroxybenzene, or the nickname, the trivial name is phenol. It is called PHENOL, phenol. Okay. Now we know this oxygen atom, it has two lone pair of electrons. Now for delocalization to happen, this oxygen, we know it is electronegative, but it has two lone pair of electrons. So this lone pair, one of the lone pairs, it will jump over here, it will form a double bond. So I will get one resonance structure. Oxygen, hydrogen, the lone pair is still there, but after the formation of double bond, this oxygen acquires a positive charge. Okay. And then if this double bond is forming, then this gets disturbed. This double bond gets disturbed temporarily, and it falls on this carbon. Okay, so I will draw this structure like this. Okay, and then these two electrons are here with a negative charge, and there's a double bond here, there's a double bond here. Okay, then again. Now again the movement will happen. This this electrons will form a double bond here. To disturb this double bond, electrons fall over here. So another structure is possible. So I will get OH, a lone pair, positive charge, double bond here, and then the ring, the benzene ring, like this. Double bond is here, two electrons, negative charge, like this. Again, after that, this will fall over here. This will fall over here on the carbon. So I will get another structure like this. So that is phenol, oxygen carrying positive charge. And finally, I will get one more structure like this over here, two electrons over here. Again, I can have this electrons falling over here and these two electrons going back on the oxygen. So I'll get a final structure over here, OH with its two electrons on oxygen, single bond over here, and then the benzene ring. And now the position of the double bond has changed. Compare this and compare this one. See, in here the position of the double bond is different, here it is different, but they are after resonance. After the resonance, you will see the position of the double bond has changed. So this movement of the pi electrons, it is called resonance. And if we have more, if we have more resonating structures, if we have more resonating structures, if we have more resonating structures, then the then the compound, whatever compound it is, then the stability increases. Stability increases. Stability increases. So remember this. So that is all about resonance. Now, after this example, benzene. If you come back to benzene, if you come back and look at benzene, benzene will have only two resonating structures. Only two. One is this one, and another one is this one. Another one is this one, this way and this way. So these are the two resonating structures of benzene represented by A and B. Only two. So stability is less if you compare to phenol. Now this can also be represented in this way also. Instead of putting the double bonds in two different formula, we can just put a circle in the center. Okay, that is the resonating structure. That is the canonical, we can say. These are canonical forms. Okay, this is the hybrid. It is the resonance hybrid. So this structure is called resonance hybrid, and these two structures are called canonical forms. Canonical canonical forms for the structure of benzene. Okay, now after this, I've been talking about aromatic. Now, what is aromaticity? That is more important to understand. Okay, now let me introduce one more thing over here for aromaticity, explaining you the word aromaticity. Aromaticity, aromaticity. Now, over here under aromaticity, please keep in mind benzene. Benzene and its compounds, derivatives of benzene, they behave they behave differently as compared to aliphatic compounds. They show unusual stability and they resist addition and oxidation reactions. If there are functional groups like OH on the benzene ring, or NH2 on the benzene ring, or Cl on the benzene ring, that is going to directly affect the behavior of this these compounds of benzene. And this behavior, which is slightly different from the aliphatic compounds, it is termed as aromaticity. Now, to understand aromaticity properly, there is a rule. There is a rule which is called Huckel, Huckel, which is called Huckel rule. Which is called Huckel rule. Huckel rule. There is a formula in the Huckel rule: 4n plus 2. 4n plus 2. It is also called 4n plus 2 rule. It is called 4n plus 2 rule. Now this n, it can be 1 or 2 or 3 and so on. Okay, now let us apply this. 4n plus 2 will tell us how many ring is possible. Okay, now say let us take for example benzene. Let us take example benzene. Okay, there are 3 pi electron pairs. 3 pi electron pairs. Now just what you have to do is, for one ring, it is a one ring, so I put the value of 1 in this formula, 4n plus 2. 4n plus 2. So 4 plus 2 is giving how much? It is giving 6. So benzene has 6 pi electrons. It has 6 pi electrons. For one ring, if there are 6 pi electrons, then the compound is aromatic. Then the compound is aromatic. Okay. This is one example. Okay. Now let us look at naphthalene. Let us look at naphthalene. One ring, two ring, and three ring. So for here benzene, the value of N is 1. For naphthalene, if you look at naphthalene, the value of N is how much? This is not naphthalene. This is anthracene. Value of N is 3 over here. Let us check now. Let us put the value of N is equal to 3 in the formula 4n plus 2. So if you put the value over here 3 for the 12 plus 2 is how much? 12 plus 2 is 14.
14.
So we get 14 pi electrons. I'm getting 14 pi electrons for a 3-membered ring, which means for a three tricyclic ring, for a compound to be aromatic, it must have 14 pi electrons. Let us check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is also aromatic. This is also aromatic. Okay. This was benzene. This was anthracene. Sorry, it was anthracene. Now let us talk about naphthalene. Okay, naphthalene. I missed out naphthalene that time. This is naphthalene. So alternate single double bonds like this. Now there are two rings over here. So I'll put the value of N is equal to 2. Okay, and I'll just apply this formula 4n plus 2 rule, and value of N is 2. 4 to the 8 plus 2 is 10. So I must get 10 pi electrons. There should be 10 pi electrons. Then only this should be aromatic. Let us check. 2, 4, 5, 6, 7, 8, 9, 10. So this is also, this is what? What is this? This is naphthalene. naphthalene. Naphthalene is also, it is also aromatic. It is also aromatic. But what is not aromatic? Let us first try to apply the formula to those also. Okay. So I hope this slide is clear to all of you. Huckel's 4n plus 2 rule, my dear students. Is it clear? Now, now
Yes, sir.
let us see another example. One-membered ring. A one-membered ring I am drawing over here. It is like 4 carbon atoms. I put a double bond here. I put a double bond here. So this compound, it is called cyclo. It is called CY cyclo buta 1,3 diene. Now, for a one-membered ring, you should have how many pi electrons? You saw in the previous slide. For one membered ring, you should have how many?
6.
6. You should have 6 pi electrons. But is there any 6 pi electrons? Only 1, 2, 3, 4. There are only 4 pi electrons. This has only 4 pi electrons. So is this aromatic? Is this aromatic?
No, sir.
No, it is non-aromatic. Non-aromatic. So this is how you try to find out. Let us take one more example. Another example. Let me take octa one. 8 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 carbon atoms. Alternate single and double bonds. I'll put one double bond here, then one here, then one here, and one here. So this compound, it is called cyclo. It is called cyclo octa. If I start numbering from anywhere, 1, 2, 3, 4, 5, 6, 7, 8. So it becomes cycloocta 1, 3, 5, 7. Tetra in. 4 times double bond, no? So tetra in. So now this compound, it has one ring. Value of N is equal to 1. For the compound, for a cyclic compound which has one ring, it should have how many pi electrons? It should have 6 pi electrons. But here, count the number of pi electrons: 2, 4, 6, 8. It has 8 pi electrons. This compound has 8 pi electrons. So this compound is also non-aromatic. It is also non-aromatic. So this should help you classify aromatic and non-aromatic. So the rule, you remember the formula 4n plus 2 rule, or which is also called Huckel rule. For value of n is equal to 1, the number of pi electrons should be 6 pi electron. For value of n is equal to 2, the number of pi electrons should be how much? We calculate it. It should be 10. It should be 10 pi electrons. Okay, 10 pi electrons. Uh, and if the value of n is equal to 3, the number of pi electrons should be 3 4s are 12 plus 2 14. 14 pi electrons. Are you getting it? So this is how we try to classify and clearly state whether a given compound is aromatic or not. Am I clear with this, all of you? Am I clear? So
Yes,
this
sir.
is how you're going
Yes,
to
sir.
distinguish between aromatic compounds and non-aromatic compounds by looking at the formula and applying the Huckel rule. So if the question is asked which rule helps us to distinguish between aromatic and non-aromatic compounds, the answer should be Huckel's 4n plus 2 rule. We call it Huckel's 4n plus 2 rule. Am I clear? Am I clear, my dear boys?
Yes, sir.
Okay. Now, now come down to the next slide. Aromatic hydrocarbons. Okay. Now, chapter in detail now. Now, we have already studied in hydrocarbon introduction in this chapter that aromatic hydrocarbons are a special type of hydrocarbons. Most of the aromatic hydrocarbon contains benzene ring. Benzene is a highly saturated hydrocarbon. You cannot put any more multiple bonds. But in a majority of reaction, it does not lose its unsaturation. Now, substituted benzene. Look at this. When a hydrogen atom of benzene is replaced by any other atom, then benzene becomes a substituted benzene. So, for example, if you take benzene over here, this is benzene, and we know there are hydrogens, 6 of them. There are 6 hydrogen. Normally, we don't write hydrogens in the ring, but I'm just writing them down. If I replace any hydrogen, take it out, remove it, and put over there maybe a methyl group or a chlorine atom, then that becomes methoxy. That becomes, this is not methoxy. This is methyl benzene. Okay, this is methyl benzene. This one is methyl benzene. So this methyl benzene, the nickname, the trivial name, which you must learn and get used to is, it is called toluene. It is called toluene. It is called toluene. Okay. So CH3 C6H5 is toluene. Are you getting it? You must have heard of TNT. Have you heard of TNT? Explosive. TNT. It is an explosive.
Yes,
High
sir.
definition explosive. Trinitrotoluene. So that is how, if you get methyl benzene, then you can prepare toluene by following certain temperature, pressure, and conditions and laboratory equipment. So trinitrotoluene looks like this. One substitute over here, and then the alternate double bonds, one nitro group here, one nitro group over here, one nitro group over here. So this is the explosive I'm talking about, trinitrotoluene. Okay, so it is also a substitute derivative of benzene. Okay, now if you replace that one of the hydrogen atoms by chlorine, then you will get chlorobenzene. You will get what? You will get chlorobenzene. Okay, now what class do you have in the next period?
The maths.
Yes.
Mathematics.
Okay, so I think the bell has already gone, so I will just stop over here. Okay, but whatever I've done today, please revise it before the next class. Otherwise, you will become, you will become staring at the ceiling at your houses. You will not understand anything. So just go through whatever I've taught by looking at the video and going through the PowerPoint slide also. Okay, so just hold on. Record your
Yes,
attendance.
sir.
Let me record your attendance, and then after that you can what do you call join the mathematics class. Okay, just a second.
Yes, sir.
Okay, just a minute. Okay, attendance is downloaded. Thank you so much. Have a nice day.
Thank you, sir.